Electric potential due to a finite line of charge. A rod of length L located along the x-axis has a total charge Q and a uniform linear charge density lambda. Find the electric potential at a point P located on the y-axis, a distance a from the origin. So we have a finite line of charge, length is L. At a distance a from the origin on the y-axis, we want to know the potential due to this finite line of charge. If we pick a charge element dq here at a distance x from the origin, you can see that this will be at a distance r to point P, where this r can be calculated using this right triangle. R is square root of a squared plus x squared. Okay, so let's start with writing the potential due to dq. The potential due to dq at point P is k dq divided by square root of a squared plus x squared. That is basically our r. R is a squared plus x squared square root. So what is dq? It is lambda, the uniform charge density, multiplied with dx. So this will be k lambda dx divided by a squared plus x squared square root. And this lambda is the total charge q divided by the total length L, because it's a uniform charge distribution. It's a constant. Okay, so the total potential at point P will be the integral from 0 to L k lambda dx divided by a squared plus x squared square root. And for lambda, I substitute q divided by L, the uniform charge density lambda, multiplied with integral from 0 to L dx divided by a squared plus x squared square root. So I'm going to concentrate on this integral. You try to evaluate this integral, and then I will multiply it with kq over L. So in order to perform this integration, I'm going to let, let's say, x is equal to a tangent theta. So I have to make this transformation so that dx is equal to a secant square theta d theta. That's the derivative of tangent theta with respect to theta. Now, what is square root of a squared plus x squared in that case? So a squared plus x squared square root is then a squared plus a squared tangent square theta square root, which is a times square root of 1 plus tangent square theta. 1 plus tangent square theta is secant square theta. So this is basically a times secant theta, which is, remember, 1 over cosine theta. So this integration then becomes integral from theta minimum value to theta maximum value, which is to be determined. For dx, I substitute a secant square theta d theta, a secant square theta d theta. For the bottom part, I substitute a secant theta. So you can see that these a's will cancel, and I'm going to get rid of one of the secant thetas here. And this will be now the integral from theta minimum to theta maximum d theta, secant theta d theta, which is d theta over cosine theta. So it's the derivative of 1 over cosine theta. In order to perform this integral, I'm going to multiply the top and bottom with cosine theta. This will become cosine theta d theta divided by cosine square theta. Okay, now cosine square theta is equal to 1 minus sine square theta, because sine square plus cosine square is equal to 1. So this integral is then theta minimum to theta maximum cosine theta divided by 1 minus sine square theta d theta. At this point, I'm going to make a transformation to variable u. U is equal to sine theta, so that du is equal to cosine theta d theta. Therefore, this integral will become u minimum to u maximum du divided by 1 minus u squared. Okay, now how do I perform the integral of 1 over 1 minus u squared? So let's concentrate on 1 over 1 minus u squared. This can be written as a constant a divided by 1 minus u and a constant b divided by 1 plus u, because 1 minus u squared is the product of 1 plus u and 1 minus u. Now, if I write this with the common denominator, you can see this will become a plus au plus b minus bu divided by 1 minus u squared. Now you can see that this is equal to 1 over 1 minus u squared. So we are required to have a plus b must be equal to 1. And also a minus b has to be equal to 0, which tells us that a is equal to b, therefore a equals b equals 1 over 2. Okay, then the potential at point P is the integral u minimum to u maximum 1 over 2 multiplied with 1 over 1 minus u plus 1 over 1 plus u du, which is 1 over 2 natural logarithm of 1 plus u minus the 1/2 natural logarithm of 1 minus u. Why minus? Because we have a minus sign here. If you take the derivative of this with respect to u, you will obtain minus 1 over 1 minus u. So we introduce this minus sign to get plus 1 over 1 minus u. And this will be evaluated between u minimum and u maximum, which we need to determine. So in 1 over 2 parentheses, we have the difference of two natural logarithms. So this becomes natural logarithm 1 plus u over 1 minus u, which will be evaluated between u minimum and u maximum. And for u, I substitute u is equal to sine theta. So this is basically 1 over 2 natural logarithm 1 plus sine theta over 1 minus sine theta, which will be evaluated between theta minimum and theta maximum, which are to be determined. And you can notice here that this can be written as 1 over 2 natural logarithm. If I multiply top and bottom with 1 plus sine theta, this is going to be 1 plus sine theta parentheses squared, and at the bottom I have 1 minus sine squared theta. This is to be evaluated between theta minimum and theta maximum, and this is equal to 1 over 2 natural logarithm of, you can see I have the square of something here, 1 plus sine theta over cosine theta squared. Okay? And this will be evaluated between theta minimum and theta maximum. So this square term will come out of the natural logarithm and get rid of the 1/2, and I will be left with natural logarithm of 1 over cosine theta plus sine theta over cosine theta, which is tangent theta. So I remember that x was a tangent theta. Therefore, I have tangent theta is equal to x over a. What about cosine theta? Well, if I form a right triangle here, I can figure out what cosine theta should be in that case. If this is theta and this is 90 degrees, x over a is tangent theta, a squared plus x squared square root is the hypotenuse. You can see that from this triangle, cosine theta is a over square root a squared plus x squared. But what I have in the natural logarithm is 1 over cosine theta. So the potential at point P becomes a natural logarithm of 1 over cosine theta, which is square root of a squared plus x squared over a squared plus x squared square root over a, plus tangent theta, which is x over a. And this will be evaluated between x minimum and x maximum. Now x minimum is 0, x maximum is equal to L, the length of the rod. So I can substitute these values. I obtain natural logarithm of, so I have the common denominator a here, you can see. X is equal to L plus a squared plus L squared square root over a, minus x is equal to 0 gives me natural logarithm of a over a plus 0. Natural logarithm of 1 is 0. Therefore, I obtain my final answer. Potential at point P is, now remember I have KQ over L here, so I have to put that KQ over L, and then I have natural logarithm L plus a squared plus L squared square root divided by a. So this is my final answer for the potential at point P due to the finite length rod, which is uniformly charged. Okay, so let's take this answer and have a discussion in the limit L is much less than A. So if L is much less than A, this should turn into a point charge or A is much greater than L, so I'm very far away. So this looks like a point charge at a very far distance. So let's see if that works. If L is much less than A, we should have a point charge. So the answer, natural logarithm L plus A square plus L square square root divided by A, can be written as natural logarithm of L plus A square plus L square square root minus the natural logarithm A, because it's a division. And for this part, I need to do nothing. I can only consider L much less than A for this term. So natural logarithm of L plus A square plus L square square root in the limit L is equal to 0 or L much less than A. Now I'm doing a Taylor series expansion. First term, I substitute L is equal to 0. So this is going to be natural logarithm of 0 plus square root of A square plus second term, I take the derivative with respect to L. So it is 1, derivative of L with respect to L is 1. Then I have derivative of square root of A square plus L square. I obtain a 1/2. The derivative of inside is 2L. Then I have A square plus L square to the power minus 1/2. And then this has to be divided by itself, L plus A square plus L square square root. And this will be evaluated at L is equal to 0 multiplied with L minus 0. So that's the second term in the Taylor series expansion, and this goes on like that. So you can see that the first term is natural logarithm of A. The second term, when you substitute L equals 0 here, this disappears, and I'm left with basically 1 over A multiplied with L. So this is L divided by A. So that the potential at point P becomes KQ over L. Then I have, for this term, natural logarithm of L plus square root A square plus L square, natural logarithm A plus L over A, and then I have minus natural logarithm A. So minus natural logarithm A. These two will cancel, and I will be left with KQ over A. So potential at point P will be KQ over A, which is the answer for a point charge located at the origin. Okay, so that's basically what it looks like in the limit L much less than A. It turns into a point charge at the origin. All right, so let's summarize what we did here. We considered the electric potential due to a finite line of charge length L. So first thing we did is we put this on the xy plane so that the origin is at one end, and at a distance a from the origin on the y-axis, we're interested in the total potential due to this finite length line of charge, which is uniformly charged. So we take a charge element dq, which is the charge density lambda multiplied with dx. It's at a distance square root of a squared plus x squared to point P, and the potential due to that is k dq over square root a squared plus x squared, where dq is lambda dx and lambda is for uniform charge distribution, total charge q divided by length L. So to find the total potential, we have integral from x goes from 0 to L, k lambda dx over square root a squared plus x squared. For lambda, we substitute q over L. This is an integral from 0 to L dx over square root a squared plus x squared, which is a tricky integral. In order to perform this integral, I do a change of variables. I go from x to theta as x equals a tangent theta, dx equals a secant square theta d theta, and square root of a square plus x square becomes square root of a square plus a square tangent square theta, which is a secant theta. So for dx, I substitute a secant square theta d theta. For square root of a square plus x square, I substitute a secant theta. I'm left with integral of secant theta d theta, which is integral of d theta over cosine theta, which is integral of cosine theta d theta over cosine square theta if you multiply top and bottom with cosine square. And for cosine square, we can substitute 1 minus sine square. So this turns into cosine theta d theta over 1 minus sine square. Then another change of variables, sine theta is called u, so that du is cosine theta d theta. So I have du over 1 minus u square as the integral I need to perform. For this case, I can basically write 1 over 1 minus u square, as I have shown here, to be 1 over 2 multiplied with 1 over 1 minus u plus 1 over 1 plus u. So that's what I did here. So now I can recognize this integral as minus natural logarithm of 1 minus u, and this integral is plus natural logarithm of 1 plus u with the 1/2 in front. So this will be evaluated between u min and u max. Since I have a minus sign with the common factor 1/2 here, this is natural logarithm of 1 plus u over 1 minus u. And u is sine theta, so it's natural logarithm of 1 plus sine theta over 1 minus sine theta. Now I multiply top and bottom with 1 plus sine theta, so that this becomes 1 plus sine theta parentheses squared divided by 1 minus sine squared theta. 1 plus sine theta multiplied with 1 minus sine theta gives us this result. And 1 minus sine squared theta is cosine squared theta. So I have 1 plus sine theta over cosine theta parentheses squared. This comes out of the natural logarithm. 1 cancels the 1/2. I'm left with natural logarithm of 1 plus sine theta over cosine theta. Okay, so 1 plus sine theta over cosine theta is 1 over cosine theta plus sine theta over cosine theta, which is tangent theta. Then I remember that I called x as a tangent theta, so tangent theta is x over a. Then cosine theta is a over square root a square plus x square. 1 over cosine theta is square root a square plus x square over a. So that's what I substitute here. For 1 over cosine theta, for tangent theta, I substitute x over a. The limits of the integration are now 0 and L. For x values, this is the length of the rod. So then I have for L, square root of a square plus L square plus L over a. For 0, I have natural logarithm of square root of a square over a plus 0. Natural logarithm of 1 is 0. So I'm left with this answer, natural logarithm of L plus square root a square plus L square over a. That's the answer to the integral, but the overall answer has a kq over L prefactor. So it's kq over L, natural logarithm L plus square root a square plus L square divided by a is the answer. Now I want to check the limit when L is much less than a. Does this behave like a point charge? Well, this answer, the natural logarithm part, can be written as natural logarithm of top minus natural logarithm of the bottom, which doesn't have an L in it. So in the limit L goes to 0 or L is much less than a, I have to evaluate the first term. I do a Taylor series expansion. First evaluate the function at L equals 0. L equals 0 gives me natural logarithm of a square, square root of a square, which is a. Then I take the derivative of the function with respect to L. 1 plus 1/2 power comes up front, 1/2. Derivative of inside 2L, a square plus L square to the minus 1/2. Now, natural logarithm of a function f is f prime divided by f when we take the derivative. So that's going to be L plus square root A squared plus L squared at the bottom, which is to be evaluated at L equals 0 multiplied with L minus 0. The other terms will be L minus 0 squared, L minus 0 cubed, etc. But it will be sufficient to consider these first two terms. When evaluated at L equals 0, this disappears and this gives me just 1 over A. And there is an L here, so this is L over A. Natural logarithm of A plus L over A minus natural logarithm A, these will cancel, so this will give me just L over A. KQ L over L, L over A, L's will cancel. I will be left with KQ over A as the answer. That is precisely the answer for a point charge.